Okay, we are back to recording. Are we back to not broadcasting? Let's see if we can. We seem not to be broadcasting. Let's do it again. Okay, so what we're about to do was check that for n greater than or equal to 4, 2 to the n is less than or equal to n factorial. And we're going to do it by induction. And so let's just remind ourselves. So I expect everybody knows that when you want to prove something by induction, first you check a base case. And this is one of these situations where, which case you should take as the base case. It's clear here, but it's not n equals 1, or n equals 0, which would be one of your normal base cases. No, here you should really do it at n equals 4 because that's when it starts happening. So this should be your base case. And there we've already checked it, right? I mean, base case n equals 4, check that indeed it's true that 2 to the 4th is less than 4 factorial because this one's 16 and that one's 24, and we checked it. Good. So in the inductive step, all right, this is how you always do inductions. We'll expect you to do these things on the homework. And people were suggesting in the chat how we should do this. Yeah, so given, I'll just take a cue from something that someone just wrote, but basically everybody's been saying the right thing. Given that 2 to the n is less than or equal to n factorial, and in fact, it's even a strict inequality, right? For some previous value of n, say n greater than or equal to 4, then 2 to the n plus 1, right? Well, that's 2 times 2 to the n, right? So that went up by a factor of 2. What we want to say is that the n plus 1 factorial went up by a factor of more versus n factorial, right? And so it went up by a factor of n plus 1. In other words, this is going to be less than or equal to, in fact, less than n plus 1 times, oh, maybe I should, sorry, let's do this a little more systematically. So we can use induction to say, okay, this is less than or equal to, even strictly less than 2 times n factorial. Let's use the inductive step, the inductive hypothesis right there. Right? And again, how are we using it? The point is, we took a 2 and we multiplied it by the inequality 2 to the n is less than or equal to n factorial. We had that inequality right there. We multiplied it by 2 in order to get that one. Right? Yeah, we're assuming it for, we're assuming we have it for n. We're trying to show it for n plus 1. Thanks for clarifying that in the chat. That's correct. Right. Someone wrote k rather than k and k plus 1, or n and n plus 1. It doesn't matter what we call the name of the step. And then the point is, I'd like to say, oh, 2 times n factorial is less than or equal to n plus 1 times n factorial. And that we have to justify, right? And why do I want to justify that one? This one is n plus 1 factorial. Getting crowded. Here we go. Give ourselves some space. So this was by inductive hypothesis, and this one I'm claiming is going to be since 2 is less than or equal to n plus 1, right? We took, here we had a 2 times n factorial, and here we had an n plus 1 times n factorial. And how do we know that 2 is less than or equal to n plus 1? Because n is at least 4. And this thing looked messy. Let's get rid of that. Okay. Okay, so what did we do? We began with assuming the statement for n, and we concluded it for n factorial. Oh boy. We got a string of equalities and inequalities. They gave us that. Okay, let me read a few things in the chat here. Okay, I think we're okay, but any questions before we move on? So at this stage, I'm going to go back to that string of inequalities. In fact, I'm just going to copy them here. So we've shown, in fact, maybe that's just the end of that proof. Yeah, maybe I'll say that was the end of the proof for the inequalities, but I really want to analyze the growth of these things. So we've shown that what n choose 5 is less than or equal to n choose n over 2, less than or equal to 2 to the n is less than or equal to n factorial, and this was true for n large. But really, how big are they relative to each other? I want to get really a sense of their asymptotic growth as a function of n. But really, how quickly do they grow as a function of n? Oh, I don't want to write n factorial, I want to write n question mark. Let me emphasize this. And so let me tell you a little bit about the answers here. So first of all, one of them is really on your homework. Let's start with the n choose 5, or this could have been any fixed k rather than k equals 5. You have a homework problem that says this thing is between n to the 5th over 5 to the 5th and what is it? N to the 5th over 5 factorial. Really, the homework problem says if you fix a k, then n choose k is bounded between that lower bound and that upper bound. And if you think about it, that's actually telling us something pretty precise about how n choose 5 grows as the n gets large. This thing is n to the 5th over, what is it? 3, I wrote in my notes, 3,125, but check me on that. That's what 5 to the 5th is. This one is n to the 5th over 120. And so the point is n to the 5th is growing like a constant times n to the, excuse me, n choose 5 grows like some constant times n to the 5th. Now, I'm gonna write it like this. Grows like c times n to the 5th for some constant c. And right, this is showing that it grows like greater than or equal to 1 over 3,125 times n to the 5th. This one shows it grows less than or equal to in size 1 over 120 times n to the 5th. And so in computer science, the way they would say that is, oh yes, it's omega times n to the 5th, which means there's some constant that you can put in front that it's less than or equal to that constant times n to the 5th, excuse me, greater than or equal to that constant times n to the 5th. And it's also less than or equal to some other constant times n to the 5th. That's what we've shown by showing those inequalities here. In fact, it grows more like this one. So in fact, the upper bound is more correct. Since it's exactly n times n minus 1 times n minus 2 times n minus 3 times n minus 4 divided by 120. That you can check, right? This is some polynomial in n whose leading term is going to be an n to the fifth. If you wrote it out, if you expand it all out, it'd be n to the fifth minus something plus something in lower powers of n. It's approximately going to be like n to the fifth over 120. So that really is a pretty precise picture of the growth of n choose 5 as n gets large. Okay. So once you've done the homework problem, then you should be good in terms of understanding that one. This guy, though, so this is, it's definitely much less than this thing, is we know a formula, n factorial over n over 2 factorial times n over 2 factorial. So it's like n factorial over n over 2 factorial squared. And what I'm going to show you is below, right, we're going to do this using Stirling's approximation, why this thing really grows much faster. It doesn't grow like an n to the fifth times a constant. This one really grows almost like a 2 to the n itself, except we have to divide by a square root of n, and then I have to put a constant up here, which is almost 1. It's the square root of 2 over pi. So let me emphasize this. What I'm about to say below is going to be from Stirling's formula, Stirling's approximation. Let me just crowd it in here, and then we'll do it on the next page. Okay, I think what I'm going to do is on the next page, I'm just going to start writing these things again. N choose 5. This thing is approximately equal to, we decided, n to the fifth over 120, 5 factorial. It, I claim, is quite a bit less than n choose n over 2, which we decided is n factorial over n over 2 factorial squared. And that is going to be using Stirling, which we haven't talked about yet. It's going to be about like 2 to the n over a square root of n, and I have to throw a constant in front, which is about 1. That's kind of messy. Let me write that again. Okay. And so the point is, when we want to compare that with 2 to the n, now we can understand it pretty well. Here's 2 to the n. Well, this is 2 to the n, and you're dividing by a square root of n. So these half-sized subsets, oh, Adesh, you raised a hand. Thank you for being polite. Yeah, what's your question, Adesh? You want to unmute?
Yeah, so I just wanted to ask, you know how you said the upper bound is a more representative formula for it. So is there like a formula, like how do you characterize the tightness of a bound?
Yeah, so let me say it this way. When I wrote it there was an imprecise way. In fact, what I'm saying is the limit as n goes to infinity of that thing divided by the thing that I'm using as a bound is 1. In other words, as n goes to infinity, this numerator and this approximation that we put in the denominator, the ratio is approaching 1.
I see. Okay, that makes a lot of sense.
Yeah, and that, if you use that formula that we had on the previous page, you could just show that. This is like a calculus problem, right? n minus 1, n minus 2, n minus 3, n minus 4 divided by 120. And then the thing in the bottom is, oops, you would be able to do that, you know, using L'Hopital's rule or whatever. So we could have written the more precise thing and proved it there too. Good question. Okay, so let me put in a little bit of separation here. I'm getting a little messy. So this really lets us get a good sense of how the size of the half-size subsets versus all subsets grow relative to each other. Like I said, this thing is about square root of 2/3. That's almost 1, and it's a constant. And it's really that there's a factor of about 1 over square root of n between these two answers. Okay. And then the 2 to the n, I mean, we have a sense of how big 2 to the n is. We talked about how many digits it has, base 10. So let's say that's something that we understand. You know, it grows every step by 2. What about the n factorial? Well, again, that's something that maybe we don't quite have a sense of how it's growing, but Stirling's formula is exactly addressing how this thing grows. So let's say this is Stirling's approximation. And what does it say? It says n factorial grows about like, okay, as a first step, it's about like n to the n, but not quite. It's n over e raised to the n. And then there's there's sort of a constant factor, a square root of a 2 pi, but there's also a square root of n under the square root sign. So the way I like to think of it is, oh, it's about like n to the n. Well, not quite. It's n over e to the n. And then there's that square root of n in front and some constant. Okay. But the point is, it gives you the sense, oh, really, n factorial is growing much faster than 2 to the n. At every stage, right, this thing grows about like a 2. This one grows about like n over e at each stage. And then there's a little bit of growth just from the square root of n plus 1 versus square root of n. Mostly, I think of it as like, oh, it keeps going up by n over e. And when the n gets large, that's much bigger than, you know, growing by the 2. So, okay. So we definitely need this to understand asymptotics. We need the approximation for n factorial. Okay, so this is theorem 221 in the book. They don't prove it either, but proving Stirling's approximation it's not so hard. It's just like kind of a long calculus exercise. In fact, you often see it in the appendix to many calculus books. They do it as an application of the ideas in calculus. So what does it say for n large? It's exactly what I was writing there above. N factorial is about n over e raised to the n times this extra factor, which is this constant times square root of n. And this, again, is that same meaning I was writing above. The limit as n goes to infinity of n factorial divided by the approximation really is 1. As n goes to infinity, the ratio goes to 1. But as an application of this, let me explain why Stirling would imply this estimate for the half-size binomial coefficient. So let's actually steal that. Oops. So this is really corollary to Stirling. And what we were saying up there was really true, that n factorial is about that. And let's just, use Stirling. The point being that this n, choose n over 2, we've got these factorials in the numerator and the denominator, and now we can approximate the factorials with Stirling. Yeah, William says the double integral looking thing is a sideways approximate equals. Yep, that was true. Don't know where I did it, but this thing. Yes, that was supposed to be approximation. This is approximately equal to this. Yep. Good. So let's just check this. n choose n over 2 is on the nose equal to n factorial divided by n over 2 factorial squared. Sterling says, all right, we can approximate those n factorials and those n over 2 factorials as the n gets large. For the numerator, it's saying, yeah, what was it? N over e raised to the n times the square root of 2 pi n. That's Sterling for the numerator, n factorial. Okay. And for the denominator, I replace n by n over 2 when I'm doing my factorials. So it's n over 2 divided by e raised to the n over 2. And it's a square root of 2 pi n over 2 under the square root sign. And then that whole thing was squared. So maybe it looks like a mess, but no, it's not so bad. Let's just keep going. What do we got? We got an n to the n. We're going to have an e to the n. We're going to have a square root of 2 pi n. Okay, so that's just rewriting what's happening in the numerator. And in the denominator, what have we got? First of all, what's the power of n? I see an n, and I see it's getting raised to the n over 2. So let me start there. What else have I got? Oh, I like this. You see this? There's an e. It's getting raised to the, oh, I got that wrong. Let's be careful. You know what? Let's do the denominator more slowly. Let me square everything. That's the mistake I was making. I was forgetting to put that squaring in with that n to the n over 2. So I'm going to bring that squaring into everybody. I've got n over 2e now raised to the n because I had an n over 2e, used to be raised to the n over 2, but then it got squared. Okay. This stuff, under the square root sign, I had 2 pi n over 2, so that's just like a square root of pi n, but then it's even getting rid of the square root because of the squaring. So make sure I didn't make a mistake here, but I think this is, nope, it's without any square root sign. Almost made a mistake. Pi times n, seem right? Okay. Now let's try to get rid of some things. I see an n to the n here and here, so those go away. I see an e to the n and an e to the n. They go away there. Am I getting this right? Oh yeah, and then there's a 2 to, right. This 2 to the n was in the denominator of the denominator. So that's a 2 to the n. Yeah, that's where this guy's gonna come from. So I think I got a 2 to the n times this square root of 2 pi n over pi n. Okay, and right. So I see a square root of n divided by an n. That's like a square root of n in the denominator, as I was expecting. And what's left is a square root of 2 pi divided by pi. That's a square root of 2 over a square root of pi. I think it's okay. Let me see what I did. I mean, it wasn't fun, but it was just kind of straightforward once we had the Sterling approximation. Good. Oh, I realized I forgot to do something when we came back from the break. You all like put yourselves out there, at least 22 of you did, and told me what your birth date was. And I didn't tell you, yes, 2 of you actually have the same birth date. It seems 2 people were born on April 11th. I'm not saying who, right? Nobody sent anybody any cards, but it appears that a couple of people in class have April 11th as a birth date. That was actually pretty good because when we come back to analyze the birthday paradox and do the counting, yeah. So when we go back to do the analysis, what I'll tell you is that when it's 22 people, as in our case, approximately the chance that that everybody would have distinct birthdays was about 0.53, so about 53%. So it was only a 47% chance that two of us would have had the same birthday. Actually, I didn't even count myself. If I had put my birthday in there, that would have been 23 of us. But let's just say the 22 of you. So we had a 47% chance of it happening, but it did happen. So anyway, it's the point of the birthday paradox is it's a higher chance than you would think. And so like the fact that it actually, happened in our class, that had a 47% chance that it actually happened. So that's pretty good. 22 people for 365 days out of the year is right around the break-even point. I think when it's 23 people in the room, you go past a 50% chance that two of them will have the same birthday, which is kind of surprising. So anyway, just didn't want to keep you in suspense about that too much longer. So we aren't going to do it today, but let's come back and analyze that birthday paradox later. Thank you for giving me your birthdays. Okay, so everybody good with our asymptotic analysis here? Let me just summarize again. We had the n choose 5, the n choose n over 2. We had the 2 to the n, and we had the n factorial. And so the point is we got these much less. This is about this. This one is about what we just figured out. Square root of 2 over pi, which is some constant, times 2 to the n over square root of n. This one's a 2 to the n on the nose. And this one's like an n over e to the n up to some small modification. Okay, questions before we move on to some other material from chapter 3? All right, let us move on. So chapter 3, we're going to do some binomial, multinomial coefficients and identities. This is also going to relate to something we'll talk about later, the technique of generating functions, which is a rather cool way to understand more counting. So it deals with some counting problems that initially seem rather difficult. Okay, so let's start out with something that I think a lot of people have seen, basically the binomial theorem. Well, let's also do the multinomial theorem. So the way I'm going to phrase the binomial theorem is I take a binomial, something that has two terms, and in this case, the variables x and y, just adds them up, but then raises them to the n. So x plus y is a binomial. And it expands it using binomial coefficients. That's why they're called binomial coefficients. And it says, oh, it's the sum as k goes from 0 to n of, when I multiply this out, this x plus y to the n, every term is going to look like x to a power, call it k, that's between 0 and n. And then the y is going to have to be the complementary power. It's going to have to be y to the n minus k. And there's going to be a coefficient in front, and that's our binomial coefficient, n choose k. Oops, kind of looks a little messy there. N choose k. All right. And let's just think about this for a moment. This thing, it's total degree in x and y. If you think of x and y as just being their degree 1, this thing is going to be of degree n because we took a degree 1 thing and we raised it to the n. So it's no surprise that when we expand it out, each monomial term is going to be of total degree n, x to the k, y to the n minus k. It had to be. But the question was, what's the coefficient? And more generally, right, there's this multinomial theorem. What do we get? It says, what if I've got many variables, not just an x and a y, which are two variables, x1 plus x2 plus, and I think I'm going to use L variables, x sub L. So that's a multinomial. It's got many terms. and I raise it to the nth. Can you see that in? I raise it to the nth. And the point is, again, it's going to be a sum of x1 to various power, x2 various power. These monomials that have the variables raised to various powers, k1, k2 up through kl. Okay. They're non-negative powers, right? This thing, when I expand it out, I'm just going to get non-negative powers of x1 through, x1, x2, and xl. But again, the point is, if I think of each of those variables as being a degree 1 thing, this whole thing is of degree 1, the sum of them. And when I raise it to the nth, I'm going to get a bunch of terms that are of degree n. So that means these exponents, they better all add up to n. So they are non-negative. Let me write that. K1, K2, up through KL are, let me emphasize that they're integers and they're non-negative integers. So this thing that I've written here just is a set of non-negative integers. The non-negative integers. Non-negative has 2 n's in a row. It's always confusing. But not only are they non-negative, they better sum to n. Right? Because the total degree here is going to have to be the same as the degree of the thing on the left. Everybody see why that is? And I haven't put the coefficients in front. I've just said, okay, it's going to have to look at like some kind of a sum like this. And the point is, the coefficient you stick in front is what I call the multinomial coefficient before. And choose K1, K2, KL. And we had some formula for that, right? We wrote down this thing was n factorial divided by K1 factorial, K2 factorial, KL factorial, just like this one was n factorial divided by K factorial, n minus K factorial. But my point is, whether we had a formula for it or not, let's see why these would be the appropriate coefficients that go in front of these expansions. Okay, so let's try to think about how we might prove this. You okay so far? All right, so proof. Well, let's do the binomial one first. Let's just be concrete about it. So this is going to be sort of proof by example, and I hope you'll, if you believe it in the example. So let's do the example where n is 5, x plus y to the 5th. Why is this thing equal to, blah, 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 plus a term. Okay, I want to look at the x squared y cubed term, right? This is k equals 2 and n minus k is 3. Why is this? Why should that term have a 5 choose 2 in front of it, the x squared y cubed term? Let's just think about that. And if we understand that, then I think we'll get the general picture, right? The point is, here I've got k is 2. We're definitely using here n is 5. Okay, so let's try and understand that. And the point is, you just think about writing this thing out. As 5 parentheses that have been multiplied together. Right? I put them together. And I think about those parentheses as being like, parenthesis number 1, 2, 3, 4, 5. And so the point is, how are you going to get terms multiply out x squared y cubed? Well, the way you expand this thing out, right, is to get the monomials, is in each parenthesis you pick, oh, which am I going to take, x or y? Maybe I'll take x, 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 and here I'll take y and y. Right, as Thea is saying, the point is I've got these 5 parentheses and I have to pick out which subset of 2 of those parentheses do I take x's from, maybe this one and this one. And then from the other ones, once I said, oh yeah, from that one and that one I take x's, then it's in the other ones that I take y's. Okay? So it's 5, choose 2. You just pick which 2 parentheses get the x's. I'll make it this one. And the rest of them, you pick the y's. Everybody see why that's 5, choose 2? Okay. And let's think about this one then. Before I flip this page, everybody okay with that explanation for the first formula, the binomial theorem? Okay. So to prove this one, again, of course, I'm going to do it by example. Let's think about y is, I don't know, x1 plus x2 plus x3 to the n equal to, all right, so again, now I'm going to be, here L is 3, so I'm looking at these non-negative integers, k1, k2, k3. This is x1 to the k1, x2 to the k2, x3 to the k3. I'm claiming it's going to be these trinomial coefficients, so multinomial coefficients that have 3 things on the bottom. They better add up to n. Let's think about why is this true? And so I, again, want to think about this as that guy is, there's n parentheses. Right, so they're going to be labeled 1, 2, nth parenthesis. And the point is that you have to pick, in order to get this particular monomial popping out, right? The way we expand this thing is we say, oh, I'm going to pick a term from each of these. You know, maybe from these first 2, I'm going to take the x2. And then from this one, I'm going to take the x1. And all those other parentheses, I got to make a choice of which one I'm taking, either x1 or x2 or x3. And if you think about it, you have to choose, like, maybe you say it like this, okay. Choose, I don't know, k1 of the parentheses to pick the x1. Maybe that was one of them. And then there's another, I don't know, maybe there's, whoa, that got a little crazy. Maybe there's another, choose k2 parentheses to pick the x2. So like this one and maybe this one. And it looks like I didn't give myself any parentheses to pick x3s, but I should have, right? And then maybe there's, you know, some, I don't know, maybe there was some intermediate parenthesis that I missed in there, you know. Choose k3 parentheses to pick the x3 from. And so if you realize what you're doing is you read from each parenthesis, which is it going to be? Am I taking an x1 or an x2 or an x3? You're reading off a word of like x2, x2, x1, x3, x2, x1, x3. You know, you're just reading off a word like that. And that word is going to contribute to this particular monomial if and only if the letter x1 appears k1 times in the word, the letter x2 appears k2 times in the word, and the letter x3 appears k3 times in the word, right? So this is same as picking a word of length n with k1x1s, k2x2s, k3x3s, which is one of the things that we said was counted by n choose k1, k2, k3. It's these rearrangements of three letters, x1 and x2, x3, with k1 copies, k2 copies, k3 copies. Seem okay? Okay. We have gone over a little bit in our time. I guess not too much because we started at the 22 after. Any questions before we do more stuff with binomial theorem? Oh, sorry, next time. Any questions before I turn off the recording? The plan is next time we will do some consequences of binomial theorem. We'll use it to get identities. We'll learn how to prove things this way. But any questions before I turn off the recording and we move into office hour? Okay, recording is going off.